Good afternoon, everyone. I'm Catherine Brookman, Associate Director, Knowledge Transfer and Exchange, and on behalf of Dr. Jack Callahan, Director of the Center of Research Expertise for the Prevention of Musculoskeletal Disorders, or CRE-MSD as we are more commonly known, we'd like to thank you for joining us today for this free webinar on AI and markerless motion capture for ergonomic assessments. We're grateful to the Ministry of Labor, Immigration, Training, and Skills Development for our funding, which supports the delivery of these webinars, and to our presenters who provide their expertise. CRE-MSD has recently switched video conferencing platforms and is now using Zoom to host these webinars. Please bear with us should we need to address any technology issues that occur during this webinar. This webinar will be recorded, with the recording being made available to you along with the presenter's slides shortly after today's webinar. Participant names will not be visible in the recording of the webinar. The format of today's webinar is as follows. The presentation will be given, after which time we will have 10 to 15 minutes for a question and answer period with our presenter. Please refrain from using the raise hand button, as we will not be monitoring this feature or any other meeting reactions. During the question and answer period, we ask that you type your questions into the chat. The chat feature can be pulled up on your screen by selecting the chat button in the control panel that appears near the bottom of your screen. I will relay these questions to Dennis, our presenter, or a similar question should we have duplicate themes. Your video is disabled and you will be muted for the entire presentation to ensure there is no background noise disruption. Should you, however, have a pressing question or a technology glitch that cannot wait until the end of the presentation, please type this into the chat, as we will be monitoring the chat and we will do our best to address it right away. After the webinar, you will be sent an evaluation link. Please fill this out, as it will assist us in the future delivery of our webinars. Thank you so much for joining us today, and if you've not already, please check out our redeveloped MSD Prevention Guideline for Ontario website at msdprevention.com. Now it is my pleasure to introduce to you our presenter today, Dr. Dennis Larson, and tell you a little bit about him. Dr. Dennis Larson is currently a postdoctoral research in Dr. Stephen Fisher's Occupational Biomechanics and Ergonomics Lab at the University of Waterloo. Dennis is a practicing certified associate ergonomist working with Pro Ergonomics, Inc. Driven by a passion for analyzing human movement and its associations with potential injury risks, specifically in the lower back region, Dennis completed a PhD in biomechanics at the University of Guelph with Dr. Stephen Brown. He investigated how back muscle fatigue and lift movement retraining influenced lumbar spine motion control during repetitive lifting tasks. With the seemingly exponential growth in machine learning, artificial intelligence, and computer vision, and its potential integration with ergonomic analysis tools, Dennis' current postdoctoral research work, funded by WorkSafe BC, aims to understand and develop best practice guidance for integrating computer vision approaches into ergonomics assessment tools. This will help us to determine if automation of risk assessments using these computer vision approaches are both valid and feasible in the workplace. Dennis is committed to combining his biomechanics expertise, research skills, and ergonomics knowledge to reduce the burden of musculoskeletal disorders and injuries in the workplace. Thank you so much, Dennis, for agreeing to do this webinar, and now over to you.
Perfect. Thank you, Catherine, for that introduction. This is a very hot topic in the field of ergonomics right now, so I'm very happy to present some of the work that we have been working on over the past year and a bit. Before I get started, I do want to Just shout out to all of our industry partners who we've collaborated with over this project, without whom we wouldn't be able to have a data set that we could assess compared to a lab grade approach. And to our partner, Dave Brody from Cargill, for his insights throughout this project, and to the MSD Solutions Lab for funding this work as well. Now, to start off, I want to briefly introduce markerless motion capture and computer vision and how they work. So these technologies incorporate machine learning algorithms to identify key points on the human body from two-dimensional images or videos. From here, there are a variety of different methods to go from 2D to 3D and create a human pose estimated skeleton or stick figure that can be overlaid on the video or on the bodies in the video itself. And this can be done through multi-view or multi-camera approaches, or also using single view or single camera approaches. So just to give a couple examples here, I'm going to start off with a multi-view method, or the use of multi-view or multi-camera methods. So on the left, we have Thea Markerless. Now this requires at least 6 cameras of viewing the participant to reconstruct their pose estimated skeleton on top of the participant in the videos themselves. And on the right, we have an example of open pose, which you can use 2 to 3 camera views to determine key points in 3D space. Now, in order for the multi-camera systems to function, you need to perform a calibration procedure or have calibration steps so that the cameras know where they are in relationship to each other, where they are in global space, and to develop a relationship between the 3D position in the world and the 2D pixel coordinates on the videos or images that they're seeing. Now, in comparison, the single view methods, these use just a single camera. That could be a video camera, it could be your phone, just viewing the task from one specific view. And these methods do not require any calibration steps. So it seemingly creates a more increases the ease of use and applicability to the workplace. Now, with the rapid emergence of these new single camera computer vision based technologies, it is becoming more accessible to simply point and record videos of workers doing the jobs or tasks in the workplace, and then taking these videos, uploading them to computer vision programs or apps, and have them perform human pose estimation, which essentially means we are determining the position and orientation of the workers' body segments in space. And as we can see in this image here, it's just one video being uploaded, and it's overlaying this skeletal or stick figure on top of the body. Now, this can be used to provide a very rich amount of data, both time series data for body position and joint angle as the workers are completing their tasks. And this is data that we have struggled to capture in the field previously in both time and cost efficient manners. So this data, or these tools, the aim of them is to help practitioners and ergonomists better evaluate ergonomic risks in the field. However, because this technology is so new and rapidly growing and evolving, there are many questions surrounding their best use and how to apply them in the field. And these questions surround these topics of, is there an optimal viewing angle for improved pose estimation accuracy? What if we are filming from multiple different sites? We have multiple different people trying to film the same tasks. Are these going to be from the same camera view? Maybe they are, maybe they aren't. But how might this affect the ability to interpret the results that are coming out of these data? Does the speed of motion or the pace of the motion influence any image blur, which then goes on to influence any of the pose estimation accuracies? And lastly, do the outputs differ depending on the different pose estimation approaches that are out there? Now, I'm sure many of you are familiar with this guidance for observation-based postural assessments. Well, one of our end goals with this project is to create a document like this that basically outlines the current practices of using the computer vision technology and provides recommended best practices for areas of future development and improvement. And by answering the questions that I just went through in the previous slide, we can start to develop these best practices for use. So the project that we set out to complete and basically answer the question of, among healthy, able-bodied individuals performing a series of simulated occupational tasks, does the angle of video recording, the task pace, or the computer vision approach influence estimated trunk or shoulder elevation angles relative to angles estimated using a lab grade approach? So for this study, we had 40 participants involved. They completed 6 different tasks, which I'm going to get into further detail in the upcoming slides. They performed each of these tasks 3 different times at both fast and slow speeds. And the fast speed was double the speed of the slow trials. For 3 of the tasks here, we worked with Dave Brody at Cargill and looked at some videos and got some data to figure out some of the task line paces that are seen in the field. And we use that as benchmarking for determining our fast and our slow speeds. And for the other 3 tasks, we basically looked at what could be possibly done as fast as possible without causing a lot of errors or mistakes and can be controlled within the lab. And then the slow speed was half of that. So getting into the specific tasks that we included. So we're going to start with above shoulder work. So in this task, participants needed to sort key tags of varying colors from pegs that are located about shoulder height up to pegs that are located above their shoulders. So there was 16 tags altogether, and they were set up so that there was a symmetrical amount of movements on the right and the left-hand side. And they did this at both the fast and the slow speeds. Going to the next one I'm going to talk about is the cart pushing and pulling. So here we had a cart that was built with an instrumented force transducer in the handle, and we put 50 pounds of weight on the cart, and we pushed it along this taped track forward and backwards 5 times. And again, this was, or 5 times, and this was paced by the speed of a metronome. Jumping to some of the lifting tasks. So we have the floor to shoulder lift. So here we lifted a crate that had 10 pounds of weight in it, lifted it up onto a shelf that created the hand height at shoulder level, and then back down to the ground to the beat of a metronome, fast and slow speeds, again, 5 different times. For the palletizing task, we had a simulated palletizing setup where participants were instructed to move crates with the same amount of weight as the lifting task that we just saw, move the crates from one side of the force plates to the other. And we had set it up so that there was some close reaches and some far reaches and a little bit of asymmetrical work as well. All of the stack on the left, the participants turn to the left in order to complete or transfer the crate over. And then all the stack on the right, participants turn to the right in order to stack the crates on the other side. Now, next we have the cutting and trimming task. So this white block that you see on the table here, this is based off of a meat trimming and cutting training block that Cargill uses to train their employees. So we 3D printed a replica of that and got participants to go through the motions of cutting and trimming that they would do, similar to what they would do as training at Cargill at both fast and slow speeds. And then last is packaging. So here we simulated a packaging type task where you're working at a workstation and you have participants loading containers of Play-Doh into a box. So there was 10 containers there. And then once they were done, they slid the box over simulating moving the box along a conveyor belt or from one side of the workstation to another to simulate completion of the task. Now, for all of the tasks that we captured in this data or in this study, we had 8 synchronized videos capturing video data from 8 camera angles all the way around the participant. So we had some in the front, or a camera anterior, camera posterior, camera to the left, camera to the right, and then at 45-degree offsets between the frontal and sagittal views. Now, all of these data from these 8 cameras were pre-processed through Theia Markerless. And this gave us our pose estimated reference data that we used to calculate the trunk and shoulder angles that used as our reference data for comparisons of the computer vision tools. And just to give an example of what this looks like, this is a palletizing example. I'm going to let this play through a little bit, but you can see how the multi-camera system generated key points, so those kind of white dots on the participant, and there's enough data there to generate 3D coordinate systems at each of the segments on the body. And this is a point that I'll come up to later in the presentation as well. Now, like I mentioned, we had 8 cameras capturing videos, synchronized video from 8 different camera views. And we took each of these 8 cameras and processed them through 4 to 5 different pose estimators. So here's an example just of a side view of that palletizing task with the 5 different pose estimation companies that process the data. And here is an example. I think all the videos are running. There we go. So here's just an example of all of the pose estimation companies on the same video, the same task. So I want to, as you're going through and watching this, I want you to think about how each of the companies has their own set of key points, and they're setting up their own skeletal structures, or not skeletal, stick figures over top of the participants. And this is, again, another point that I'll come up to a little bit later in our presentation, but they're all doing it a little bit differently. Now, for our actual comparisons, we took the Theia data, we brought it into Visual 3D, and from Visual 3D, we extracted shoulder elevation and trunk flexion extension angles. Those same angles were captured from the pose estimation data as well. So like I said, we took all 8 videos, sent them to the pose estimation companies. They processed them, sent us the data back for the trunk flexion extension angle and shoulder elevation angles. And we brought them together to make our comparisons. So this is just an example set of, say, 3 camera views from one pose estimation company compared to Theia. So this is just an example showing how we run these comparisons. Theia right here is in the black bars, and each of the camera views are the different colors of lines. And over the entire data series, we determined root mean squared differences between each of the camera views, all of their angle data compared to the Theia data set. So again, for all camera views, all companies, all trials, all videos, we ran a root mean square difference. So we determined the difference between each of these camera views for each of the companies. Like I said, we calculated this difference. And I want to point out that many researchers in the field would coin this metric as a root mean square error, but we are calling it a difference. And the reason for this is that the skeletal or stick figure pose estimation overlays that are going on top of the videos, they are estimating the position of our underlying skeletal structures. And they may not be exactly replicating the bony movements that are happening as we perform all the tasks. And this is the same for optical motion capture approaches too. We put reflective markers on bony landmarks that we palpate, but the skin moves on top of this, so there's skin movement artifact. So again, we're doing our best to estimate the motion of our skeletal structures. So because our reference system is estimating the body positioning in space, we can't say with 100% confidence that this 100% replicates the skeletal movement that's happening within our body. So from that, we can't say anything deviates from this reference is an error, but we can say that there is a difference. So that is why we called root mean squared difference instead of error for this measure. Now, before jumping into some of the results from the study, there is a lot of data here. So we are still in the final processing stages and double checking of data for a couple of the companies. And I think for a lot of us or all of us on the team, we didn't fully understand the sheer amount of data and data processing time that this study would take when we started this project. And it has been an incredible learning experience working our way through some of the roadblocks that we had to overcome to get where we are currently. But I just wanted to point that out, that we're still in the process of finalizing some of the data. But that being said, I aggregated the results from 3 of the 5 companies to showcase some of the emerging trends that we are seeing in the data so far. And due to the time constraints and not wanting to overload the presentation with too much data, which, although I may have already done, I'm only going to present a subset of data from 3 separate tasks. So we'll kind of walk through each of the tasks slowly and look at a subset of the shoulder elevation and trunk angle measures in each of them. So to begin, we're going to be looking here at left shoulder elevation during the above shoulder work task. Now, for all the figures that you're going to see in the upcoming slides, we have camera angle on the x-axis from anterior left, all the way around to anterior right. So all 8 of those camera views. And we have root mean squared difference on the y-axis. What you're going to see pop up is a fast, or 2 bars for each camera angle, a fast and a slow. Fast is represented by the dark blue, light blue is represented, or slow is represented by the light blue. Now the first data point that I'm going to bring up here is from the left camera view. And I'm going to only populate this one for now, but this is the lowest RMSD or lowest difference of the 3 companies that we looked for compared to Thea for this camera view. So this is the best camera view for this task, looking at the left shoulder angle. And I also want to point out, because I forgot to mention it, there will be letters on top of all the different bars. On all the bars that statistically compare the difference between different camera angles. If you have a letter of the same, or if the bars have the same letter on top of them, they are statistically similar. If they have different letters, they're statistically different. So I forgot to mention that, but you'll see that coming up in a few slides, and I'll remind you when we get back to the slides in a bit. But what I want to point out here is we have a 10% or 10 degree root mean squared difference between Thea and our computer vision companies, the 3 that we looked at. And before I move on with any of the results, I kind of want to jump back from this initial result. And I want to address what might be a little bit of an elephant in the room regarding this 10 degree difference. So what I'm going to show you here, it's the left shoulder elevation above shoulder work. This is just the elevation angle across the entire trial from a representative trial that I pulled out for the left camera view. So here, this is the reference Thea data of the left shoulder angle as they complete this task. And as I populate this graph with data from all 5 of the companies, so I'm going to slowly populate the graph here. I want you to see that there are general offsets or biases in some of the data at time points throughout the trial. And some of these are above, some of these are below. And we believe that these general offsets and biases are due to differences in how the joint angles are being calculated between the different companies and between Thea. So there's differences there, and I'm going to get into that a little bit more. So as I mentioned at the beginning of the talk, Thea requires a multi-camera setup with video and image data coming from at least 6 cameras to generate a 3D human pose estimation and overlay on the participant. With all of this data from all the different camera views, the Thea system can represent body segments like the upper arm, like the torso, the pelvis, thigh, etc. They can represent these segments using 3-dimensional coordinate systems, of which we know the position and orientation in space. I can then calculate shoulder elevation and trunk flexion extension angles following ISB standards, which many researchers use to calculate these angles, unless other conditions are needed to be met. Now, with single camera pose estimation, there may potentially, or these companies may potentially use open source computer vision approaches like the 2 that I've shown here, OpenPose and MediaPipe, or they may have developed their own approach to pull out or identify key points in 2D space on each of the camera views or videos that were provided. They have then built and trained their own machine learning models to pull these data from 2D into 3D, and each company has developed their own model with their own set of training data. And what they do is they pull these data into 3D, generate the 3D coordinates, and they connect vectors between these coordinates and calculate angles between these vectors. Now, what we've learned is that each company, like I said, has their own approach to calculating and defining these shoulder elevation and trunk angle calculations. So while we tried to best match our calculations with the Thea data set to all of the companies that were involved in the study, the way that we are calculating these angles with Thea is still inherently different compared to these companies, which leads to the general biases and offsets that we're seeing between the computer vision companies and the Thea data sets. So right now, that means although we're comparing, trying to compare similar joint data, we're still comparing a little bit of apples to oranges in this case. So now that I've hopefully cleared the elephant in the room, we have an explanation for this general root mean squared difference that we are seeing between the computer vision companies and our reference data when we're looking at optimal viewing angles. We can now refocus to other factors such as the camera angle and the movement speed that may influence the overall accuracy of the single camera computer vision data. So we can focus on these additional factors that we want to figure out what are some best practices for. So coming back to this figure here, again, we have our best or optimal viewing angle from the left for the left shoulder. And on the anterior right side, this is where we saw the largest RMSD difference between Thea and the computer vision company or companies. So what you can see here is that they have different letters on top. So they're statistically significantly different from each other. And the partial or an explanation for this is that if we look at this image here that I popped up, this is the view of this above shoulder work task from the anterior right. And if we're looking at the left shoulder, we can see that that is partially occluded during this task. So coming in and out could lead to some greater deviations and differences from for the computer vision companies compared to Thea. Now here's the rest of the camera angles, and you can see they populate and go in between these 2 extremes. And so what I'm going to be pulling from here is there's a key takeaway that a side view to the major plane of motion is performing best in this scenario. And if we avoid occlusions of view, like we avoid those anterior right and the occlusion of the left shoulder, we reduce the differences away from Thea. I also wanted to point out that there are asterisks above some of the bars here, and that indicates a statistically significant difference between movement speeds for that camera angle. So from what I can see here, these are popping up where there is non-optimal camera views. So a key takeaway from this is that the slower pace is leading to greater differences in the non-optimal camera views. Okay, so that's a lot of data. That's the left-hand side. I'm going to jump to the right shoulder for this same task. So we're just kind of flipping the views a little bit, flipping the joint that we're looking at, that motion. Same setup, we have RMSD on the y-axis, all the camera angles on the x, fast is dark blue, slow is light blue. And when we pull this up, we're looking at the right shoulder this time. From the right-hand side, we are seeing that this is the optimal camera view. So it's just the opposite of what we saw earlier. Left side, left shoulder, that was optimal. We're now seeing right side, right shoulder, that's optimal. We're also seeing that the anterior left, we're seeing that has the largest differences compared to Thea. And again, that's just because we have those occlusions like I talked about earlier. So we're having the similar results, but just flipped for the right side of the body. And then the rest of the camera views can fill in the in-between. And we can once again see that there's a statistically significant difference between the fast and slow speeds for some of these non-optimal views. So again, key takeaways here, perpendicular view to the plane of motion, we have a lower RMSD, so lower difference between the computer vision companies and Thea Markerless. We want to avoid the occlusion of view as leading to some greater differences, some potentially more noise in the data. And we also want to record motion from the same joint of interest. What's interesting here is, I forgot to point it out in the last one we're looking at the left, is that if we look at the right shoulder from the left-hand side, we're seeing elevated RMSD compared to that. So if we're looking at the right hand or right shoulder movement, we want to record from the right side of the body. If we're looking at left shoulder movement, trying to assess that, we want to assess from the left side. So just summarizing that up into a couple key take-home points. We know that video recording matters. We are seeing that it's perpendicular to the plane of motion. We want to avoid occlusions, and we want to record from the same joint of interest. So that is what we're concluding initially from this data set and from the rest of the data that we'll see coming up, and that there's limited influence of movement pace when you are recording from the optimal views. And the other suboptimal views, we are seeing those statistically significant differences pop up. Okay, so that is it for the above shoulder work. I'm going to jump to a different task now, palletizing, and I'm going to focus in on the right shoulder elevation. So right shoulder elevation, palletizing. Here's the same figure set up. So we have camera angles anterior left all the way around to the right. Room mean square difference on the y-axis. Blue is fast, or dark blue is fast, light blue is slow. Now the key difference between the above shoulder work task and this task here is that the above shoulder work is stationary, facing the anterior direction. With palletizing, we are picking up a crate, turning all the way around, putting it down. So our right shoulder is in view with the right-hand side, or right video camera for half of the task, and then it's in good view for the left-hand side for half of the task as well. So that is reflected in the data that we are seeing. So both the left and the right sagittal views of the shoulder elevation angles are producing lower RMSD differences between the computer vision and Thea Markerless companies. Whereas more of the frontal views, they are producing higher RMSD or higher differences between Thea and the computer vision companies. Now this is also, there's partial occlusions here due to the stack of the crates that's being placed in front of the person or participants as well. So again, we want to try to avoid those occlusions where possible. And one additional thing I wanted to point out here is you'll notice that there is that statistically significant difference in movement speed, but only at the suboptimal levels. So at the anterior and posterior directions, and not at the optimal views of the left and right, so the sagittal view. So again, we'll populate the rest of the camera angles that kind of fill in the middle between these extremes. And the key takeaways here again, perpendicular view of the major plane of motion is performing best in these scenarios. And we're also seeing that slower pace, again, greater RMSD in the non-optimal views. Now that is the right shoulder elevation angle. We're going to switch to trunk angle. So with the trunk angle, again, or a similar camera view or similar graph setup, here we're seeing the right and the left side, so those major plane of motions, having a greater or lower RMSD, sorry. And then we're also seeing the anterior right come into play a little bit here. And I think that's because we are seeing, as the participant is moving and turning, we are changing our camera, or moving the plane of motion into that camera view that is sagittal to the motion. And then the anterior and posterior, those are our worst case scenarios here. And then filling in, we have the posterior left and posterior right, which are just slightly higher differences compared to the what I've coined as the optimal views here. But again, as we're turning, we're changing our major plane of motion to be sagittal to a variety of different camera angles as we are going through that motion. So again, key takeaways: perpendicular view, major plane of motion, lower root mean squared differences. And then here we're seeing limited influence of movement pace in the optimal views. So if we go and look at specifically the right and the left, which I would say would be the ones that we're seeing the pop up as the most often being the best views, we again don't have the differences there. So again, this goes back and supports our key takeaways that we are finding so far. Jumping to the last trial that I'm going to look at is the packaging task. So again, same setup, same figure setup as before. And thinking about what we've learned so far, the right camera view, we're looking at the right shoulder angle, and we're doing the major plane of motion as flexion extension. And if we think about where our camera views have been best currently, or what we've seen so far, we would say that the right view is producing the best results. And that's the same thing we're seeing with this task here. And then for the ones that are having greater differences, we have the anterior and anterior left view. So again, we're not looking at the major plane of motion from the sagittal view. And we're also seeing here again that speed effect is happening in those non-optimal views. So again, I'm going to populate the rest of the camera angles that are filling in between. Again, a key takeaway: side view of the major plane of motion, same side of joint of interest. And these are similar results to the above shoulder work task as well. Now, this is where kind of things get a little bit interesting. Trunk angle during packaging. Again, I'm assuming, or I would think, based on what we've learned so far, that the sagittal view from the right and the left would perform best in this case, as that's the major plane of motion. But in this case, it is the anterior right. And a potential reasoning for this is that as we are going through the packaging task, we are turning, twisting our body and flexing forward. And that major plane of motion now is in view of that anterior right camera view. So that is where I'm thinking that this has popped up as lower RMSD compared to the rest of them. And then thinking about what is worse in this case, which is posterior right, that same line of thinking, if I'm twisting and reaching to go pick up an item, that posterior right view is looking at my frontal plane, and that is performing worse in this scenario. So although a little bit different, these results are still supporting our key takeaway that the camera angle perpendicular to the major plane of motion is performing best in this scenario. Now, what is interesting here is that we are seeing a little bit of the opposite effect in terms of speed. And that is that we're seeing slightly greater RMSD in the fast-paced movements across most of the angles here. And we're still trying to figure out why this may be. So we're still analyzing some data to figure out and build out this explanation a little bit more. But we also, if we look at the differences themselves, there may be 1 to 2 degree differences on average between all of them. So they're statistically significant, but they're 1 to 2 degrees on average. That's what it's looking like just from this graph here. So going back to the key takeaways, again, we are supporting the video, that video recording angle matters, perpendicular to the motion plane. at avoiding occlusions, and we have that limited influence of movement pace, even though we're starting to see a little bit of our limited influence of movement pace at those optimal views, although we have seen statistically significant results, specifically with the last slide that I just showed. These are on 1 to 2 degrees on average, so I'm still saying there's limited influence here. Now, to answer our last question about computer vision data, I've thrown a lot of data at you so far and a lot of figures, but I just want to throw in this initial comparisons. And again, I want to remind you that we are still analyzing data from one of the companies coming in and also double checking another data set. So this is still a work in progress, this comparison across companies, but I'm just going to throw up 2 examples here. So we have palletizing and above shoulder work. I've got them both as left shoulder elevation angles. I've reduced the amount of camera angles to look at just to make it less amount of bars on the graph. Same RMSD on the side. But what you're going to see here is you're going to see 5 bars pop up. So starting with palletizing, we see the 5 bars pop up. And on average, and generally, we're seeing that there's an agreement across companies that the left camera view is the best camera to view this major plane of motion. And going to the left shoulder evaluation or elevation with the above shoulder work, similar results. We're seeing, generally speaking, across the computer vision companies, the left view or that sagittal view is the best result across the different camera angles. So again, this is the left shoulder elevation. So I focused on the left-hand side because we want to record from the same side of the joint of interest. So a key takeaway here, similar results and interpretation across companies. And just adding that into our key takeaways so far, there are subtle differences, but similar results in interpretation across companies, meaning that we are still looking at the video, or still knowing that the video recording angle matters. And what we didn't look at in the last slide is the influence of movement pace. So that is still something that we're investigating further. So a lot of data that I just threw at you, and I want to kind of wrap things up by bringing into context of what does this mean for ergonomics now and in the future. So for what does this mean for ergonomics now? I think what this means is that using computer vision or using this technology is not as simple as point and shoot, upload a video, and Bob's your uncle, you got a completed risk assessment. Boom, to that, we're done. I don't think that's the case. With everything that we have learned so far in this project and that what we're seeing in the data that we've collected and are continuing to analyze, capturing good quality data requires training and guidance. And using that quality data can then be input into some assessments moving forward. So it's like I want to say the good data in, good data out. And as we wrap up analyzing the data for this project, we are aiming to create some sort of best practice guidance documents, like I said in the beginning of the presentation. We want some documents and infographics to help users better understand how to use the data or use these technologies in the field, how to best interpret the data and capture good quality data in the field. Now, we're also seeing that a lot of these companies are integrating single task assessment tools. These include NIOSH, Liberty Mutual Equations, REBA, RULA, Strain Index, etc. So they're building these into their platforms to build out their risk assessment capabilities. And while these assessment tools are mainly posture-based and require inputs such as frequency, duration, inputting force or the box that's being lifted to generate the risk metrics, I believe that these computer vision technologies can be used to help companies, ergonomists, health and safety practitioners perform more automated data-driven risk assessments in the field if they're capturing good quality data. So they still need to be validated to make sure that they are generating generating similar risk metrics to what we would consider to be the gold standard as what we've had before. But this generally should hopefully free up some time to focus on creating solutions for identified risks instead of spending a whole bunch more time collecting the data in the field. So hopefully speeding up the data collection part, and you can more focus on data interpretation and then creating a solution for potential identified risk in the workplace. So in principle, I think this is a great move forward in the field of ergonomics, but like I said earlier, it's not as simple as point and shoot and would require some good data as input for these risk assessment tools to be used in the field. Now, before I talk about how I want to bridge this technology to the future or how it can be used in the future, I want to put this technology in context with previous work surrounding a 2.5-year long Ontario University's back pain study. So this study examined physical and psychosocial risk factors related to low back pain in workers at General Motors in Canada, and how they to capture all the data, they've recorded videos. So they recorded videos of workers on various jobs, various tasks throughout General Motors, and they set up the camera to view the major plane of motion for the joint of interest, which was trunk flexion extension. They set it up with a side profile or that sagittal view, which again aligns with the data that we are suggesting of how we should move forward and capture good videos in the field. These videos were then digitized and an operator assessed them using a computer program, manually entered the posture information to match the stick figures in this computer program with the postures that are seen in the videos. And they did this frame by frame. And from this immensely deep, detailed data set, many seminal studies using this data set have identified several biomechanical factors associated with reporting of low back pain. So peak and cumulative loading, peak flexion velocity, etc. Many biomechanical factors associated with pain development in the workplace. And this very influential work no doubtably took a very significant amount of time and effort to collect and analyze to get to these conclusions, especially going through all the videos to posture match frame by frame. Now, bringing this back to the context of computer vision, what this means for the future of ergonomics in terms of how computer vision can be used. With this technology, we now have the ability to capture time series movement data in the workplace in a way that we had never had before, ways that we have been challenged to capture data in both time and cost efficient manners without bringing big optical motion capture systems in there or having put markers on people. This technology can help us capture those data in the field much easier. And when captured using best practice principles that we are looking into and continually learning about, this can lead to an extremely rich database of movements that occur in the workplace that are outside of just trunk flexion extension. And all these movements can then be used in various epidemiological studies to further identify and characterize injury risks in the workplace. And the one area of immediate interest is quantifying cumulative loading exposures in joints throughout the shift. So within the landscape of modern work, it is difficult, or it is changing so that the workplace is evolving more multitask work. So trying to measure cumulative exposures across multiple different tasks is becoming increasingly difficult, but we think that this computer vision technology can be used to capture the time series data necessary to help us estimate cumulative loading exposures for tissues and fatigue development over multiple different tasks. And ultimately, we believe that this technology can aid in the advancement of the multitask assessment tools that we need in the future. So now, before I turn it over for questions, we're going to get to the end of the presentation here. I do want to remind everyone that these computer vision tools have built-in machine learning models to identify key points on the human body. And these models have been trained on various videos and data sets, but they will continue learning and getting better as we feed it more data or put it through more data or give it video data that has different tasks involved. So it's seeing things from different angles, and we can then get better estimates of computer vision. So pose estimation. So given the recent advancement of this technology, I'd argue that we are still in its infancy or early childhood stage, and there's a lot of growth and learning that we still need to do in order to use them and develop these best practices for use in the field. So with that, I would like to open up the floor to any questions and thank everybody on the team for all their work and effort that they've put into bringing all this together. It's been crazy amount of work that we've had to do, and hopefully I've given enough time to answer all the questions out there. And if not, you can contact our team and we can answer them.
Thank you so much, Dennis. An amazing amount of fantastic information on such a timely topic. We've got a lot of questions and I'll try and get through them quickly. And for those that we don't get to, people can contact you or members of your team directly.
Yeah.
Can you confirm which Thea version these results were computed with?
Oh, not the newest version.
Okay.
Yeah. So it is the oldest version. I can't remember the code exactly off the top of my head, but it's not the newest one that just popped up.
Okay. Did you use IMUs as well to confirm angles?
So we do have IMUs on the participant. If you noticed in the videos, they were pushing buttons. That was the Life Booster IMU data set. We haven't received that data yet to confirm, but it's on its way.
Okay. A question around why not using a gold standard such as the optoelectronic system?
Yes, as said in a lot of our interactions, this is a very popular question. So instead, I'm going to back up here. A lot of these companies, like I said, they have trained their machine learning algorithms on different data sets. Some of them have used optical motion capture as a training tool, some of them haven't. So when we've learned or we're investigating how these companies do their pose estimation, we learned that that was a case, and we didn't want to bias any companies towards being able to pick up markers that they've been trained to pick up within the data set. So therefore, we went with a Thea marker system, which doesn't have any markers that some companies may be biased towards to improve their pose estimation compared to others.
Okay. Could you explain briefly how you take into account the differences in biomechanical model to calculate angles at different degrees of freedom?
Yeah, so we haven't looked into those biomechanical models at different degrees of freedom yet. For looking at the kind of the angles that we looked at, we initially were looking at, we were talking maybe more about comparing fruit and meat, and basically, if I'm going to put in that term, we were calculating angles relative to pelvis, which we would typically do in the workplace, or not in the workplace, in research. And we initially saw comparisons that were drastically different. So we had to work back and compare, make sure that we were calculating angles that best represented what they were calculating in the field. In terms of incorporating into biomechanical models, we haven't got that far yet.
Here's a very basic common sense question. What camera height is optimal in your study?
That is another good question. So within our study, we optimized for Thea. So Thea, they recommend anywhere between 6 to 8, maybe up to 10. I can't remember exactly, but we went approximately just under 8 feet. I think it was around the room on a track of systems. So it is looking more like a surveillance look down on the participant. So that was optimized for Thea, which was then our reference system, which we can then work back from. In terms of the computer vision tools, I don't know exactly what the optimal angle is, but that is something that we need to kind of look into in the future. But thinking about how it's used in the field, you typically would take a video camera and put it out in front of you, kind of more of at chest height. So that it provides a very different view of the person in context, or the worker in context, compared to the kind of top view that we have. And it is a potential, or it is a limitation of the work that we have here, and it's something that we can work into the next studies and address further.
Thank you. Do you plan to integrate other companies and or tasks into future studies?
We'd be open to collaborating with many companies. Like I said, there's a lot of different people doing different things out there. We've only sampled a very small portion of what is out there. So yeah, if we have other companies out there willing to help us out and figure out what we can do to make these best practices work, we'd be open to collaborations. And then other tasks, yeah, we want to build in other tasks as well. So these were very controlled laboratory tasks, very stationary in the center of the room. Whereas in the field and in the workplace, there's a lot more movement. There's a lot more back and forth, moving around, and more traffic in and out of the camera volume between other people and other objects. So these are all things that we need to continue working towards in the future. But as of right now, this was a very controlled data set, and we continue working to are basically starting from our base model of knowledge and working from there.
Perfect. Thank you. So if anyone's interested, I'm sure they can reach out to you.
Mhm.
Do the pose estimators take advantage of the reflective markers? So while this, would it interfere with its accuracy or enhance?
Um, some of the companies have been trained using optical motion capture data sets alongside videos. Others have not, or have just used videos and haven't had that optical motion capture piece built into their algorithm. So every company is different. And so some of them may be able to take the camera views with those optical reflective markers in them and be able to better estimate the pose, knowing that that's built into their training algorithms, compared to the companies that didn't use it. So there could be some differences in that, but we didn't directly assess that in this study here.
Okay. Here's another very common sense basic question. I also had this one in mind. Will you also evaluate the accuracy of the pose estimators when wearing bulkier clothing? And do you have any comments on that?
Yeah. Yeah, so in this study here, we had people or participants wear athleisure wear. It's not really representative of what's happening in the field where you have PPE and kind of, if you're in a cold environment, you're wearing a lot of protective coating, clothing, stuff like that. We haven't assessed that directly in this study, but our multi-camera system approach, the Thea Markerless, they have done some validation and reliability testing within their approach, and they haven't found any major influences of large size garments or PPE or anything like that in their computer vision program. But that is a multi-camera approach. So it is possible, I think, but we have not validated or tested it in these computer vision companies. Some of them may have already done internal validations that we don't know of. So that is something that you can reach out to any of these companies you're trying to work with and ask them if that is something that they've considered.
Okay. You touched on pace a bit before. Do you expect slower pace to have greater RMSD? And if so, why would you think so?
Yeah, so this is something, it's a good question because we've been also asking this as well. We originally thought that a faster pace movement would cause greater motion blur, which would then lead to poor pose estimation detection and less accuracy or greater differences. We are kind of seeing the opposite a little bit in our data set. And I think the reason for this is that we did not time scale our data set. So the fast trials are half the amount of data as the slow trials. So they're basically in the slow trials, there's double the amount of data. So there's just double the amount of time where those differences can be just a little bit higher and be incorporated in the root mean squared difference value or into that calculation. So that is kind of potentially why we're seeing greater root mean squared differences in the slower trials compared to the faster trials. It's just because they have double the amount of data to see those differences in.
That makes sense. Was there any comparison, and you might not have looked at this, with holding a phone / camera versus a stable tripod? And you did address the camera height.
We did a camera height to optimize Thea, but we did not look at handheld versus tripod-based cameras. So with our cameras that were hung from the ceiling or on those rafters, They were stationary and secure, so there was not a lot of movement there. So that would be representative of a tripod. And I'm assuming there's camera or movements of the phone, that could potentially lead to also some potential motion blurring outside of the differences in movement pace. But we didn't look at that in the study, so another area of future research.
Okay. Well, thank you so much, Dennis. I'm afraid we didn't get to all the questions, and I'm hoping that these individuals will reach out to you, and just encouraging everyone to join us for our next webinar, which will actually be at 4 p.m. on February 19th on improving of physical and psychosocial hazards, a participatory hazard identification and risk management toolkit, the AFIRM toolkit. Hope to see all of you again, and thank you so much, Dennis. What a fabulous presentation, great data, and very exciting implications. Thank you.
Thank you all for having us.